Okay, hello everybody. I'm very glad to be here to talk about my recent work, semi-supervised validation of EMR algorithms with noisy labels. And let me briefly introduce myself. I came from Harvard University, Department of Biostatistics, and also the Department of Biomedical Informatics. After I looked through the agenda, I find I'm the only person from statistics. So I delete all the equations and the numbers in these slides. But please bear with me if it is still very technical. So as we all know, EMR is a digital version of patients' medical records in hospital and healthcare systems. And it contains a wealth of clinical informations, including diagnosis, code, demographic, medication, lab result, and family history. I find this interesting cartoon online. And so this is a small talk between physicians about their handwriting. And EMR already significantly reduce medical errors compared with paper-based records. But unfortunately, there are still some noises in EMR labels, which is created by doctors' annotation. So my work is focused on denoise the errors in the EMR system. So let me briefly introduce two EMR systems I'm currently working with. The first one is Partners Healthcare, which is a Boston-based hospital and physician network. And in Partners RPDR, that is a patient data registry, and it gathers data from those hospitals and physicians and stored them in one place. So it can bring clinical information to a research at his fingertips. So another one is Million Veteran Program, which is funded by the U.S. Department of Veteran Affairs. So the purpose of this program is to learn how gene affect healthcare for veteran volunteers. So in both of these EMR system, we have more than millions of patients and also billions of visit level data. So given all this data, what can we do as a researcher? So here is an example of Harvard lung cancer study. So the origin data of this study is hospital-based cancer cohort. And we have about 11,000 lung cancer cases enrolled from Massachusetts General Hospital and also Dana-Farber Cancer Institute. But later the investigator merged their data to the Partners Healthcare. And so using the patients from the EMR data from Partners, we have 70,000 more patients. And after that, we link the patient data with Partners Biobank. So we have the DNA plasma data of these patients. And with all this data linked together, so we can do some research, for example, biomarker evaluation, biomarker identification for lung cancer survival and recurrence. And also we can work on development of drug effect. So, but before that, a critical and foundation step is to accurately and efficiently identify the subjects we want. That is EMR phenotyping. So for EMR phenotyping, there are two key elements. One is the patient's label annotated from doctors, and the other is features. So let me first briefly introduce what the feature look like. So it can roughly stratify into two categories. One is structured data, and the other is unstructured data. So structured data are mainly the data input in this discrete input field. For example, ICD code, lab result, medication. The unstructured data are from the medical notes and usually in free text. So after some natural language processing, we can get a structured format of unstructured data. Like this, in the table, the smoking status is extracted from the unstructured data. So after we get the features, there are some standard way to do phenotyping. So first, we do some screening of the EMR system, that is the inclusion or exclusion of the patient, and then we can get a data mart. So using this data mart, we first do classification, that is assign the disease status of each patient in this data mart. And after that, we do validation. We compare with the gold standard label and see how well our model works. So if the model is validated, then we do the downstream study, that is the genetic association study or phenotype or phenome-wide association study. So some details about these 3 steps. So in each of step 1 and step 2, we need gold standard labels. That is the physician's annotation of patient's status. However, there are some noises contained in these labels. So first, the label is insufficient. So as we know from our phenotyping study, so there, for each patient, there are more than 600 notes, and physicians need to go over each of the notes. And usually they spend more than 1 hour per patient to annotate the disease status. So the second challenge is uncertain and inconsistent labels. So for some diseases that are hard to diagnose, so even the physician cannot give the definite disease status. For example, the polycystic ovary syndrome and bipolar disorder. So especially for PCOS, so there are almost half of the patients, they do not have definite disease status. And also, sometimes there are multiple physicians, they look at the same patient's note independently, but they come out with different results. Even after they compare their results, they cannot still get a consistent result. And when it comes to the time to event label, it is even more challenging. So sometimes investigators, they are interested in the recurrence of the patient. But the time of this recurrence is very hard to annotate. So here comes our strategy. So first, we want to borrow information from genetic data. So as we know, genetic study are our downstream study, and after we get our phenotyping result, we go to genetic study. But can we use the genetic data to facilitate our upstream study? If in the literature we have some significant effect of some SNPs. The second one is we want to develop a system that our machine learning model can assist physician to get a gold standard label. So if it is better than a gold standard label, we call it a platinum label. The next one is we want to develop a self-learning ecosystem. That is, after we get the response from our model, then we go back and improve our model. And this is our proposed phenotyping ecosystem. So compare with the previous one, the standard one, we have only 2 steps. We merge the validation step and the genetic association step. So after the screening of EMR data, we get our data mart and we go to our classification step. So for the classification step, we do it iteratively. First, we start from the unsupervised method without any labels, like clustering and some algorithm else, and then we go to validation. So if we get a good validation result, then we can go to next step. If the result is not good, we go back to the beginning and we add some labels. Then we retrain our model. But even if we have those standard labels, we do not consider it as the true underlying disease status. We use it as a surrogate. That is, we assume there are some errors in those labels. So, and for the validation step, we merge the validation with genetic association study. That is, we use one model to get our validation result and also our genetic association result. Here's some details of my model, and I will not go into the details of this. So, but if you are interested in this, and I can discuss with you more about it. And this is some numeric result. So, because in reality we never know the truth, so it is important to conduct some simulation study. And in this simulation, assume we know the true disease status. Here I use Y to denote it. And also, the physician's label, it is a gold standard. And in this result, the blue one, the blue one is from our proposed method, and the red one is the true disease status. That is a benchmark, and the green one is a naive method using directly the physician's result. So as you can see, the mean square error of the proposed method is very close to the one from the gold standard label. And if you directly use the physician's label, the error is very large. And also we apply our method to partners phenotyping algorithm. And one disease is bipolar disorder and the other is schizophrenia. So we have two sets of results. The first one is from reviewer 1, and the second one is from reviewer 2. And this is a 2x3 table. So S denote the result from the algorithm, and Y star denote the physician's label. So if the physician cannot get a definite status of this disease, I use 0.5 to denote it. So as you can see, for reviewer 1, there are 22 patients. They do not have a definite label. And for reviewer 2, it is very different. So they cannot get a consistent result. And by applying our method, we get a very different result from only using the physician's gold standard label. And here is our model evaluation. So perhaps I should stop here.